Okay, let's look at example 9.12. Determine the moments of inertia, the mass moments of inertia of steel forging with respect to the XYZ coordinate axes, knowing that the specific weight of steel is 490 pounds per foot cubed. Okay, so this is actually a relatively simple problem, but there's just you just have to keep track of everything. Make sure you're using mass when you should be using mass. You're using weight when you should be using weight, and so on. Okay, so how do we do this? Well, this is really three objects, right? You have one object here, you have a second object here, and a third object here. And it turns out with symmetry that 1 and 3 end up being the same for all their values, but we can go through and talk about that. So let's figure out, we need to figure out the mass, right? Because what do we know about the moments of inertia? You end up needing the mass, because we can come here and we can say, hey, this is basically uh, this cylinder, right? If I can draw this, plus this prism. Sorry, again, not very to scale. I'm running out of space. Plus this other cylinder up here. Okay, so again, I labeled this as 1, this is 2, and this is 3. So we can go through here, and if I can bring up, boom, we have a prism. We know the Ix, Iy, and Iz. We can look it up on the table, and we have a cylinder. We can look up Ix, Iy, and Iz here. So we have all this information here. We just need to be able to go through and figure out what's what. So let's come back to here, and let's figure out the mass of 1 and 3. So for number 1 and 3, okay, the volume is what? Well, the volume is just pi r squared times, I always call it h, that's how I learned it. And so what is that? It ends up being pi, if you look at the r, it's 1 inch squared times 3, which gives you, whoa, that's new, which gives you 9.42 inches cubed. Okay, so that's the volume of 1 and 3. And at number 2, we're going to say the volume, in this case it's just 2 by 2 by 6. Somewhere it shows that there's 6. It's 6 tall. Where do we show that it's 6? It's 2 from here to here plus 1, so that means it's 3, so it's 6, right? And so that's simply 24 inches cubed. Okay, so then we want to figure out, we want the mass, but we don't have the ability to find the mass, so we're given the specific weight. So we can find the weight, right? And so we're going to come in here and say that the weight of 1 and 3 is going to be 9.42 inches cubed times 490 pound per foot cubed. So we have feet cubed and inches cubed, so we got to make sure we take care of that. In 1 foot you have, 12 inches cubed. So the weight of 1 and 3 ends up being 2.67 pounds. But again, we don't want the weight, we want the mass. So therefore, the mass of 1 and 3 is going to be the weight. So F equals ma. Whoa, sorry. Right, so it's going to be the weight, 2.67 pounds divided by 32.2 feet per second squared. So that ends up being 0.0829 pound second squared per foot. Okay, so that's a mass of the cylinders, each not combined, but each cylinder weighs has that much mass. And then the mass, so the weight of 2 is 24 inches cubed times 490. I'm just going to divide this by 12. No, I'm not. It's 490 pounds per foot cubed and 1/12 cubed to make the units work out. And so the weight of 2 is 6.81 pounds, but the mass of 2 is 6.81 pounds over 32.2 feet per second squared. So that gives us 0.211 pound second squared over foot. Okay, so that's the mass of 2. So why do I care about the mass of 1 and 3 and 2? Because again, come back to here, I'm going to build this up one part at a time. And on the mass moment of inertia, all these you have to have the mass. This here, and again here, we have to have the mass for all these. So let's come back here, and let's figure out, I'm going to have to scroll up and we're not going to be able to see this, but we'll figure out the cylinders, okay? So the Ix for the cylinder, 1 and 3. Okay, what is it? Well, as we just saw, these are cylinders, and so it's in the same direction, so it's actually oriented the same in this, so it's going to be the 1/2 ma squared. But we need to do something for it. What do we need to do for it? We need to use the parallel axis theorem, right? This is not sitting on that axis. So we're going to come back here, and it's going to be 1/2 ma squared, but plus m times d squared. D is going to be my generic distance, right? So what is the distance? So it's from the centroid to where it is, and it's, in this case, it's just this distance right here. So it ends up being 2 inches. Now, having said all that, we need to make sure we account for all the same units. So we're going to put everything in feet, right? So we're going to say this is equal to 1/2 the mass, which was just, this is a cylinder, so that's, I'm just going to call it m1. It's this value right here, the 0.0829, but it's quite frankly just easy to write m1. The a is going to be what? In this case, actually, I'm going to pull the mass out of it both. So now it's going to be a, which is the radius, so it's 1/12 squared, plus the distance. That distance we decided is 2 inches, but we're going to put it in feet squared. Okay, so this ends up giving us a value of 2.59 times 10 to the minus third, and the units on this are pound, foot, second squared. So that's Ix of 1. Now, I kind of glossed over something. Let's talk about this for a second. That's Ix of 1 and 3. So of 1, what is this distance, right? This distance is in reality minus 2, but since you're squaring it, it ends up being the same. So because of the symmetry, because you're squaring all the distances, 1 and 3 have the same values. So now let's look at Iy of 1. So Iy, again, we're going to go back to look at the chart here. And the y is going to be here, 1/12 m 3a squared over plus l squared. So it's 3 times the radius and then plus the length squared. So let's come back here and we say Iy is going to be 1/12 m1, and then it's going to be 3a squared plus l squared. Okay, but we're not done yet, because again, we need to use a parallel axis theorem. And so what are we moving? This is relative to the y-axis. So relative to this axis, see if I can draw this clearly. Relative to this axis, how far away is the centroid of these points? Well, you can actually go through and figure out if this is 3 inches and this ends up being 1 inch. So this ends up being, up to this point right here, is 2.5 from there to there. Okay, so this needs to be plus m1 times, again, I'm going to put just the generic distance squared. So this ends up being 1/12 m1 times 3 times 1/12 squared, plus the length in this case is 3 inches. So 3/12 squared, right? Plus m1 times, and then here we want to go the distance from there to there, so that is 2.5 inches. Again, we got to put over 12 squared. So Iy1 and is the same as Iy3, and it ends up being 4.17 times 10 to the minus third, and same units, pound, foot, second squared. And so lastly, we need to figure out Iz is, and let's come back to this thing, and hopefully you remember this, the iz and iy are the same here, right? So we have iz and iy are the same, but what's the difference going to be? It's going to be, so it's going to have 1/12 m1, and it's going to be 3a squared plus l squared, but plus m times d squared. Now, so it's m1 times d squared. So what is that d here? Well, here it's the distance from the z-axis, so from this axis to the centroid, right? And so that's going to be different. That's actually going to be the x squared plus y squared. Now, just for clarity's sake, let's think about what this is. Let's put in these numbers. So we're talking about 1/12 m1, 3 times 1/12 squared plus the length is, what is it, 3 or 2? The length is 3, stop, please stop, 3/12, sorry, squared, plus, that's a squared, plus m1 times the distance. Now the distance in this case is the square root of x squared plus y squared, but we're squaring it, right? So it works out that it just ends up being x squared plus y squared. So what is x squared? X squared is going to be, again, that 2.5 inches squared, and y squared is going to be the 2 inches squared. And so we have 2.5 over 12 squared plus 2 over 12 squared. And so iz of 1 ends up being 6.48 times 10 to the minus third, again, pound foot per second squared. Okay, so I'm going to just highlight these or underline these right here. So there's our ix, iy, and iz. So why are we doing this again? Let's not lose track of what we're doing. We're trying to find the ix, yz, and the ix, iy, and iz of the entire system. So we need to add them all up because it's a bunch of components. We just found it for this one and this one. So now we need to find this one, and then we need to add them all up. Okay. So again, we have the mass of 2 right here. We're going to use that. I'm just, for clarity's sake, I'm just going to keep on writing m2, but I'm actually going to be using that number. And let's look at 2. I wonder if I can get away with squeezing it in here. Let's see if we can squeeze it in here. Okay, so ix of 2. What is ix of 2? Well, let's go look it up. Now we're talking about a prism right here. So it's 1/12 b squared plus c squared, 1/12 c squared plus a squared, 1/12 a squared plus b squared. Okay, so the key is here, we're not oriented quite the same way. But if you look at this, ix, right, relative to this axis right here, it's 1/12 and then b squared, so it's the two distances, b squared and c squared, the two distances that are not parallel to the x-axis. And that's true for y. You'll notice iy, so it's going to be c squared and a squared, right? And iz is going to be b squared and a squared. So coming back here, ix, and the nice thing about this, fortunately, is that it's actually centered at the centroid. So fortunately, we don't have to use a parallel axis here, which makes life a little bit easier on this one. So it's going to be 1/12 m2, and then it's a squared plus b squared. So what are the two distances for x-axis? Well, the two distance relative to this x-axis is how tall it is, which is 6/12 squared, right? And relative to the z-axis, which is 2/12 squared. So this gives you a number of 4.88 times 10 to the minus third, and that's pound foot second squared. Now I'm going to skip y for a second and look at iz of this one. Again, you'll notice it's a 1/12 m2, and it's the x distance, it's just 6/12 squared plus the x distance, which is 2/12 squared. Hopefully you'll see that that's the same, and that is equal to that. So ix and iz are both equal to the same values, and it's just because it happens to be symmetric in x and z. And then lastly, iy is going to be 1/12 m, and in this case it's going to be 2/12 squared plus 2/12 squared. So iy ends up being 0.977 times 10 to the minus third pound foot second squared. Okay, so now we just need to add them all up. So Ix of the entire system is going to be this one plus 2 of those, right? Because we have 2, we have the 1 and the 3, so it's going to be 2 times 2.59 times 10 to the minus third plus 4.88 times 10 to the minus third. So Ix ends up being equal to 10.06 times 10 to the minus third pound foot second squared. Iy is 2 of these right here, so 4.17 times 10 to the minus third plus this one right here, which is 0.977 times 10 to the minus third. So Iy ends up being 9.32 times 10 to the minus third pound foot per second squared. And lastly, Iz is 2 of the Iz1 plus Iz2, which is 17.84 times 10 to the minus third pound foot second squared. Sorry, it got a little messy in here trying to fit it all in so you can see it. But the idea is there. So the idea with this one is it's not a hard problem. I would say the hardest thing about doing some of these three-dimensional problems is just keeping track when we go over here and we're looking at, if I can find it, when we're looking at these tables, you know, which axis is which, because it's not always aligned in the same way, right? And so that is arguably the hardest thing, is making sure that you're not, when you're using these equations here, when you're using these equations here, you're using them appropriately with the right dimensions. But beyond that, it's a pretty straightforward problem. That and the other problem being that you have to make sure you're actually using mass and not weight, or you're using the appropriate units as is desired for the problem.